Michael, please go ahead.
Okay, thanks for inviting. So I will talk about the sketching complexity of graph and hypergraph counting. This is joint work with John Kelleher and Eric Price, both at UT Austin. Okay, so this is the problem that we want to solve. We're given a large graph, G, and a small query graph, H, such as the two graphs shown on the slide, and we want to compute the number of occurrences of H in G approximately. One fairly standard example is something of the following sort. Perhaps my setting is the data graph is, say, the Facebook graph, and the query graph H is a triangle. And maybe I want to compute approximately the number of triangles on Facebook. This is the triangle count is a very important property of social networks. So for instance, the clustering coefficient of a social network is nothing but 3 times the triangle count divided by the number of two-hop paths, which reflects the probability of two neighbors, sort of two friends of a certain person, knowing each other. So it's a measure of cohesiveness of a network. Well, triangles are not the only graphs that we want to count in large data graphs. For instance, this very nice work of Ugander and others suggests subgraph frequencies for subgraphs of small size about 4, as an important signature of a social network. And there are sort of 4-node subgraphs play a role. Well, subgraph counting also has other applications, so in social networks, biological networks, and other networks analysis, and that's what we want to study. Now, in this work, we are interested in understanding the complexity of approximate subgraph counting on big graphs. And in particular, the standard model to look at is the streaming model of computation. So here, edges of our graph arrive in some arbitrary order as a stream, roughly like this. And as the algorithm is scanning the stream, it can only use a bounded amount of space, so bounded by S. And at the end of the pass, it should output the approximate count for the number of triangles. Well, this model is known as the insertion-only streaming model, because in this model, edges are only inserted into the graph. In this work, we're actually interested in the more general dynamic streaming model. That is, here, edges get to be inserted and deleted in the stream, and insertions and deletions are, as long as there is a valid graph at the end. So how does one design algorithms for dynamic graphs? Well, really, essentially, the only technique that we know to work very well is the technique of linear sketching. So we think of the object that is being updated in the stream as a vector x in some high-dimensional space. So maybe for a graph, it's an n-squared dimensional vector that encodes which edges are in the graph. And then the algorithm is a linear sketch. Namely, we generate a random matrix S and then maintain S times X as the updates to the edges come in the stream. The space complexity of that is just the number of rows in the matrix S.
Just to understand, so you want to approximate it in what sense? So you assume it's a dense graph, or?
No, so okay, so in this work, in this particular question, we'll care about graphs that are of bounded degree. So I'll get to that in a minute. Yes. Overall, the problem will be, given a graph that comes in a stream, or rather, given a graph that you get to sketch, output a 1 plus minus epsilon approximation to the number of, say, triangles in this graph. Okay, so good. So pretty much the only technique for handling dynamic graphs that we know is linear sketching, and one classical application is getting good approximations to, let's say, the quadratic, the L2 squared norm of the vector that is being updated in the stream. But there are exciting applications to graph problems. We know how to construct sparsifiers, spanners, and spanning trees. The reason why linear sketching is so effective in dynamic streams is, of course, that it's very easy to maintain linear sketches when edges are both inserted and deleted. So negative updates are as easy to maintain, to process as positive updates. So one aspect of the linear sketching model that will be very important for us is the fact that this model is fairly powerful, and in particular in the sketching model, one can implement various sampling primitives. You can implement them by using a hash function together with sparse recovery. So questions like sample an edge in the graph that is given as a stream of insertions and deletions can be handled using linear sketching. Okay, so dynamic streaming is essentially equivalent to linear sketching. So because of that, we're interested in understanding the sketching complexity of subgraph counting. Okay. Good. So in the rest of the talk, I will first tell you about the problem and some of the prior results on triangle counting in graph streams. This will naturally lead us to our main results, and then I will talk about some of the lower bound ideas, because this is really the main contribution of the paper. Okay, so suppose that I have a graph given to me as a stream of edges, and I want to count the number of triangles in this graph. For simplicity, we'll think of triangles right now. So what is a very natural approach? One very natural approach is just to take a sample of the edge set of the graph and then find triangles in the sample. Now, one immediately realizes that the variance of such a process could be quite high. What if one edge has a huge impact on the triangle count of the graph? And because of that, there has been a number of works that try to parameterize the space complexity of the triangle counting algorithm in terms of the triangle degrees of edges of vertices. So for instance, one assumes that the triangle degree, the maximum number of triangles that a given edge participates in is fairly small and bounds the efficiency of the algorithm in terms of this parameter. So the paper of John and Eric from Soda 17, for instance, gives some of the nice bounds in this vein. Okay, well, on the other hand, examples of this form seem a little bit unnatural because in real graphs are fairly sparse, and it's unlikely that most of the subgraph counts are contributed by a single edge or by a single vertex. So in this work, we're interested in understanding the sketching complexity of subgraph counting in bounded degree graphs. So from now on, I will assume that my data graph G, in which I want to count subgraphs, has max degree bounded by some d, and I will assume that d is a constant. In fact, everything generalizes to an arbitrary d. There will be some poly d dependence in the bounds, which I will hide for this talk. All right, good. So just to set the stage, let me consider the following simple setting. Suppose that I have a stream of edges, and this is an insertion-only stream, and I want to approximate the number of triangles in the graph that is presented to me. Here's a very nice and simple algorithm of Johari and Gozzi that approximates the number of triangles in order the number of edges divided by t space, assuming that the graph is bounded degree. Yeah. Now, note that pretty much all of the triangle counting results have a space complexity of the form some function of the graph, let's say the number of edges, divided by some increasing function of the number of triangles in the graph. Now this is natural because one can show that if the number of triangles in the graph is small, sort of on the order of a constant, then a linear space is needed to approximate triangle count.
How large can the number of triangles be in a bounded graph?
In a bounded degree graph, so for us, every vertex has, say, a constant degree, so n times just n is the maximum number on the order n. Yeah, order n. If I have max degree d, then I guess n times d.
Yeah.
So this doesn't depend on d, though, right?
Right, because as I said, I will fix d to be a constant from now on, just to not have any irrelevant dependencies. So bounded degree model. Okay, good. So from now on, t will be the number of triangles. Now, of course, note that the streaming or sketching algorithm doesn't really know what the number of triangles is, but usually this is easy to get around. If you assume an upper bound on this number, then you can sort of repeatedly sample and see where your estimates stabilize. Okay, so here's the estimator that one uses to get order m by t space. One selects a uniformly random edge in the stream, and lets t be the position of the edge of the stream. And the estimator is the number of triangles that the edge participates in the remainder of the stream times m. Well, this makes the estimator unbiased, and some amount of contemplation reveals that the variance is roughly m times t. So roughly m, which is the sort of the upper bound, the maximum of the value that the estimator takes times the actual expectation, and in particular, order m by t samples suffice. Okay, to get a constant factor approximation. Also, when I talk about approximating triangle count, I will always say that I want to approximate it to within a constant factor. Everything I say generalizes to 1 plus epsilon approximations with appropriate loss in parameters.
Sorry, the expectation of the estimator is t and the variance is mt?
Yes.
Okay.
Yes. So I need the variance over expectation squared, so m divided by t. So about m by t samples will suffice. All right. Good. So, but now one notes that this is really something that one can only do in an insertion-only stream. I sample an actual edge that exists in the graph, and then collect all the edges that are incident on the corresponding vertices in the rest of the graph. So, what can one do in the sketching model where tricks like that are not available? Let's consider some simple examples. So, the first suggestion is perhaps just take a sample of the edge set of the graph at some rate p. Let the sample be e prime, and then my estimator is going to be the number of triangles in the sample. So rather, the number of triangles in the sample divided by b cubed, which is exactly what will make the estimator unbiased. Okay. Well, how small can P be in order to still get a good approximation to the triangle count? Well, one realizes that in order to have good variance, it really suffices it is necessary and sufficient to ensure that we capture at least one triangle, or at least a large constant number of triangles. This is because I made the bounded degree assumption so that the variance of this estimator is small. So what this means is that this will work as long as the sampling probability P is at least t to the minus 1/3, because there are t triangles overall. Every one of them is captured with probability p cubed, and so this will ensure that the variance is small. I get a multiplicative bound. What is the space complexity of that? Well, I took every edge with probability p, so it's m divided by t to the 1/3. So that's worse than m by t that we had in the insertion-only streams, and we would like to improve upon this. Okay, very nice. So let's try something else. So instead of sampling edges, let's try sampling vertices. So here's another estimator that is a little bit more interesting. Well, we sample every vertex of the graph independently with probability p, and collect the edges of the induced subgraph. So I let E prime be the edge set of the graph intersected with V prime times V prime. So look at the induced subgraph. Now, again, my estimator is the number of triangles that I find divided by p cubed. Now, for a slightly different reason, every triangle has 3 vertices. So I have to divide that. Good. So now, how large does p need to be in order for this to converge, to have good variance? Well, the calculation is the same, because p needs to be at least t to the minus 1/3. I want to capture at least a large constant number of triangles. But the space requirement now is much better, because I only keep a given edge with probability p squared. Both endpoints have to be in. So this improves the space complexity, or the sketching complexity of our algorithm, to m divided by t to the 2/3. And note that m is really order n here, because I'm making this bounded degree assumption. Okay, note that these are all sketching algorithms. As I mentioned before, sampling primitives can be implemented in sketching. All right, so this is very encouraging and suggests that we should work a little bit harder to improve this further. But it turns out that this is not possible. And this brings us to the main result of this talk.
Wait, Michael, I'm missing something. So we said that there is an m over t algorithm or not?
Okay, so there was an m over t algorithm for insertion-only streams. Right, but now I want to understand what one can do if I only get to access the graph in the sketching model. And in particular, one notes that whatever was being done in the insertion-only stream doesn't really, it's not easy to implement. Okay, good. So this brings us to our main results. Well, first, this simple algorithm that I outlined shows that you can approximate triangle count in a bounded degree graph in m over t to the 2/3 space in the sketching model, and we show that this is best possible. So, yeah.
Just for that one, didn't we say in the beginning of the talk that if you have one edge, sampling edges is a little dangerous, because if you have one edge that has a billion triangles
Right.
on that,
Oh, okay.
that seems to overestimate.
Yes, so that's good. So the question was, how does that go together with the example that I was showing at the beginning of the talk, where I had one edge that controlled a huge number of triangles. After that, I said that if one edge gets to control, let's say, omega n triangles, then this will be not a good idea. But we're working in the bounded degree model, so we assume that our graphs are bounded degree, so one edge can't really control too many triangles. Yeah. Okay, good. So this is best possible, and the natural question at this point is, how exactly did we get the constant of 2/3? Namely, how does this generalize beyond triangles? So maybe I want to count occurrences of a 4-cycle in my data graph that is bounded degree. Okay. Well, we showed that the right parameter to look at, so the right parameter that governs the sketching complexity of subgraph counting, is the fractional vertex cover of the query graph that we're trying to count. So what is the fractional vertex cover? Let me remind you. So suppose that I have my graph H, so let's say a triangle or maybe a star or a 4-cycle. The fractional vertex cover is the smallest amount of mass that I need to put on the vertices of the graph to ensure that every edge in the query graph is covered to the extent of at least one. So I'm trying to cover edges by vertices, and I want to minimize the amount of mass that I put on the vertices of the graph. Okay, well, if my graph is a triangle, then the optimal vertex cover size is 3 by 2. I put mass of 1 half, 1 half, 1 half on every node in the graph. If my graph, let's say, is a 4 cycle, then I can either put 1, 1, 0, 0, or 1 half, 1 half, 1 half. Let's say if I have a star, then the fractional vertex cover size is 1. I just cover the middle node. Okay, and we show that this is exactly the parameter that governs the sketching complexity. In the former case, the sketching complexity will be m over t to the 2/3, so t to the 1 over the vertex cover size, and similarly for the rest. So formally, for every graph H, we show that there exists a sketch with a target dimension m divided by t to the 1 over fractional vertex cover size. That approximates the number of occurrences of H to a constant factor. And again, all constant factors can be made 1 plus epsilon approximations. Okay, so let me just say a couple of words about the estimator. The estimator works roughly as follows. One first colors the data graph and the query graph, and using colors 1 through the number of vertices in the query graph. So we just randomly give names to vertices of both graphs. And then we do vertex sampling on the graph G, but it's not vertex sampling at the same rate, but rather now every vertex of the graph G has an associated vertex of the graph H. So we look at the amount of mass that the optimal fractional vertex cover assigns to that particular node, and we sample a vertex of G with probability, which is some parameter p, which is the space by m, raised to power that amount. And then this gives us a random vertex-induced subgraph. We count the number of colored copies of H in that subgraph. One can check that indeed how does the fractional vertex cover come into play here? For instance, one can check that the space complexity is indeed at most S. Why? Because for every edge in the graph G, the probability of keeping an edge is the sampling parameter raised to power, which is the amount of mass that was placed on one node plus the amount of mass on the other node. And this is at least 1, so the probability of sampling any given edge of G will be at most the correct space amount. Good. And some further contemplation reveals that the probability of keeping a copy of H is related to the actual vertex cover size, because we just have to keep every single vertex. And you get a product over all vertices of that copy, and that's exactly what happens. Okay, good. So this is the upper bound, and what we show is that this is basically tight. For every graph H with fractional vertex cover mu, every linear sketching algorithm that gives a constant factor approximation must use at least m by t to the 1 over mu bits of space.
So can I ask a related question? So there's a paper of Friedgut, if I remember, and Rodel maybe, that talks about counting, probably not in the stream setting. Maybe you're familiar with it, but they use a notion of fractional vertex cover.
Oh, I see. So I think there's a paper of Friedgut and Kahn, I think, that answers the following question. Suppose that I have a graph G with m edges, and I have a subgraph H. How many occurrences of H can I have in G? And the answer is m raised to the fractional edge cover number of H. So there is a difference. We're using vertex covers. And the reason is that our graph G is a bounded degree graph. If you don't have that assumption, then the edge covers seem to be more relevant for these questions. This is also related to some work in the database community, again on sort of instance optimal database joins, something also known as the AGM bound, which bounds the size of the join on a given database. Yeah. Okay, good. So these are the results for graphs. We prove similar results for hypergraphs. Although for these results there's some loss. In particular, the upper bound is exactly the same, but the lower bound has an extra factor of 2 in the exponent here. So these are not quite tight. Okay, good. So in the remaining time, let me say a few words about how we prove the lower bound. And we want to prove that the fractional vertex cover is indeed the right parameter. we start with the standard observation that any sketching algorithm yields a simultaneous communication protocol. And for instance, let me outline the proof techniques for triangle counting. So since we're doing triangle counting, then our proof will go through a 3-player communication game that we define. There are 3 players, Alice, Bob, and Charlie, that control sort of the 3 edges of the triangle, and they will communicate simultaneously with the referee. We will use Fourier analytic techniques inspired by the Boolean hidden matching style analysis of Godinsky and others, and some of the recent results along these lines. So interestingly, we'll design some new techniques for analyzing multiplayer games through Fourier analysis and for analyzing promise versions of related problems. So here's the communication game. There are 3 players, Alice, Bob, and Charlie. So here they are. And all of them are given edges of a graph. So we have a tripartite graph, which is a union of 3 matchings, MA, MB, and MC, so the red, green, and blue. These matchings are essentially permutations of, there are 3 n vertices, and the matchings are basically permutations on sets of n vertices. These matchings will be selected uniformly at random, subject to the product of these 3 permutations being the identity. This is the same as saying that our tripartite graph is a union of triangles. Now, besides the edges of the matchings, our players get bits on the edges of the matching. Bits of length n, so there's xa, xb, and xc, and the game with probability half is in the yes case, with probability half is in the no case. In the yes case, the bits that the players observe on the edges of the matching, here they are, XOR to 0 simultaneously for all triangles in the game. In the no case, they XOR to 1. So let me just illustrate. So the graph is indeed a union of triangles, and this game is in the yes case. The bits on all triangles XOR to 0. Good. So Alice, Bob, and Charlie look at their input and simultaneously send a message to a referee. The referee should guess which of the 2 states the game was in. Okay, and the matchings are random, so this is roughly what it looks like. Okay, so now what is the relation to triangle counting? Here's the reduction. Suppose that Alice, Bob, and Charlie have a sketching algorithm for triangle counting. Then what they do is, as soon as they receive their matchings, they look at the edges that have zeros written on them and sketch these edges and send the sketch to the referee. The referee combines the sketches and checks whether or not the corresponding graph had a large number of triangles. And if we were in the yes case, then we'll get about n by 4 triangles. Why? Because in the yes case, over every triangle, the bits were random, subject to XORing to 0. So with probability a quarter, we will actually see 0, 0, 0. So the corresponding graph will be a union of triangles and single edges. With remaining, okay, good. So we have a linear number of triangles in the yes case. In the no case, there are no triangles because the bits XOR to 1. So if we keep the 0 edges, we will not have a single triangle. Good. We prove that at least n to the 1/3 communication is required from Alice, Bob, and Charlie to the referee to get a constant advantage over random guessing. Why is this good? Well, note that in this particular case, the number of triangles in the yes case is omega n. So what our lower bound is supposed to, our algorithm would require n over t to the 2/3, so n divided by n to the 2/3, n to the 1/3 space, and the lower bound matches exactly that. When t is smaller, there's a tweak of the game that handles this situation. Okay, so let me just quickly sketch how the analysis goes. Well, first, it is useful to see what the players would do if they were constrained to using very simple protocols. The protocol is this. As soon as Alice, Bob, and Charlie look at their matchings, they decide on some edges on which they will want to keep the bits. They will send some of the bits to the referee, and they will forget all the other bits. So suppose that they choose, each of them chooses a subset S of edges based on the matching that they see, and they send the bits on these edges to the referee. So one example protocol is maybe Alice looks at her matching and just checks, is it true, and just conveys all the bits on all the edges with both endpoints having indices smaller than n to the 2/3, let's say. And then if the referee has a triangle that it received, a triangle such that it received all bits on the corresponding edges, then the referee can decide which of the 2 cases this game was in. So the question is, how large should the set S be? Well, let me sketch the argument. one can think about this as follows. So the challenge is the fact that the players can coordinate because they receive edges of the matchings MA and MB and MC, and these matchings are dependent. They're only pairwise independent. Indeed, this is why the interesting vertex-based sampling protocols exist. So one way of looking at this is to define the following quantities. For every vertex j, let's say on this side of the tripartite graph, we let WMA of j be the indicator that Alice keeping the corresponding edge. And we define corresponding indicators for every one of the players. And then the total communication of the players is the sum of the is the expectation over the sum of all the vertices in the parts of the graph of these indicators. Good. One can check after a certain amount of contemplation that the expected number of triangles in the referee's set is upper bounded by the following quantity. One needs to sum over all j the minimum of essentially the probability that Alice remembers the red edge going out of j times the probability that Charlie remembers the blue edge going out of j times the probability that the remaining player remembers the third edge. And I will just give the intuition here. The challenge in analyzing this is exactly the fact that the three matchings are only pairwise independent. So this is why we can understand the probability of both Alice keeping the red edge and Charlie keeping the blue one, and we have to separate out the third player. Okay, so it turns out that the expected number of triangles in the referee's set, as we show, is bounded by the square root of s cubed, which is the space budget, divided by n. And that's why the breaking point is s equals n to the 1/3, and this means that n to the 1/3 lower bound holds for sampling protocols. Okay, well, how does one use this intuition to reason about general protocols? Well, now suppose that Alice, Bob, and Charlie can sort of send generic messages to the referee. So these generic messages from Alice, Bob, and Charlie to the referee can be viewed as follows. We had the bits on the edges. Let's call the concatenation of the bits x. And Alice's message to the referee makes the posterior distribution of x be uniform over a corresponding message. Bob's message corresponds to, again, some subset of the Boolean cube of dimension 3n, and Charlie's message does the exact same thing. Now, one crucial difference here is that whereas in prior analyses, Fourier analytic analysis, one usually thinks of the uniform prior on the Boolean hypercube. Here we started out with a promise. That is that the bits exort either to 0 simultaneously over all triangles or to 1 simultaneously over all triangles. So all in all, one needs to understand the distribution of these random bits conditioned on the messages from the referee. This distribution is the product of three indicator functions corresponding to the messages from Alice, Bob, and Charlie times the indicator of times the prior. Okay, well, again, some amount of contemplation, and we show that the posterior distribution of the referee, given the three messages, on whether or not the game is in the yes case or in the no case, can be expressed conveniently in terms of the Fourier coefficients of the product of FA, FB, and FC. Now, in particular, it turns out that what one needs to do is sum up these Fourier coefficients over all the sets of, over all the odd collections of triangles in this game. So there should be a triangle here, here, like this. Good. So this is where the Fourier analysis comes in. So it turns out that one needs to understand the sum of Fourier coefficients over triangles of a product of A, B, and C. How does one do that? Well, this is where the convolution theorem in Fourier analysis comes in. We note that, by the way, here it is more convenient to work with a certain normalized Fourier coefficient, where basically the usual Fourier coefficient is defined as follows. We take the expectation over x in the cube, in the whole binary cube, of -1 to the x dot, the parity that we're interested in, times the indicator of the set f. The normalized Fourier coefficient just does the correct normalization. So by the convolution theorem, the Fourier transform of a product of three functions is the convolution of the corresponding Fourier transforms. And this reduces our problem to understanding a certain convolution, which in this case, luckily, turns out to also be a product because of the structure of the game. And this is where hypercontractivity comes in. Similarly to Fourier analytic analysis of the Boolean hidden matching problem and related streaming questions, we start by noticing that the sets FA, FB, and FC, they correspond to typical messages of Alice, Bob, and Charlie. And if Alice and Bob and Charlie communicate at most S bits, then the normalized Fourier coefficients of the typical messages satisfy certain L2 squared bounds in the Fourier domain. So this is a consequence of hypercontractivity. So for example, one specific setting says that if I sum up the squares of normalized Fourier coefficients over level 1 Fourier coefficients, that is single bits, then I get at most the amount of communication that Alice, Bob, and Charlie could use. And that's very nice because this lets us essentially massage the question of analyzing general protocols into a form that we already have done. So I already showed you, rather gave an outline of how one shows that a sampling protocol cannot solve the problem with a less than n to the 1/3 communication. And in the sampling protocol, basically Alice, Bob, and Charlie had the task of allocating 0-1 weights to the edges on the matchings that basically said, do I convey all the information about the corresponding bit, or do I convey none of it? So this consequence of hypercontractivity in the form of L2 squared bounds in the Fourier coefficients shows that essentially we just have to solve a related problem, where Alice, Bob, and Charlie now get to allocate fractional weights to the edges of the graph. And the only difference is that the weights also happen to be L2 squared constrained. But for triangles, the solution on this problem turns out to be exactly the same as under the L1 constrained version. And I think I'm out of time. So let me just say that hypercontractivity lets us argue that a generic protocol can be viewed as a sampling protocol, except that Alice, Bob, and Charlie don't just allocate weights to edges, but they also have to allocate weights to collections of edges, and the weights are bounded in L2 squared sense. A very similar counting argument as the one that I showed before shows that even under L2 constraints for triangles, the optimal solution is at most the bound on the expected number of triangles that you catch, which translates into the posterior probability of the referee, is at most roughly s cubed over n. And this gives us the result. Good. So just a quick summary. What we showed is optimal bounds on the sketching complexity of subgraph counting. And the bounds are tight for all graphs, but they're not quite tight for hypergraphs. And the reason why they're not tight is that this equivalence between the problem under L2 constraints and the problem under L1 constraints does not quite work for hypergraphs, and we will lose something there. And so that would be very nice to understand. And in general, it would be very nice to get other Fourier analytic bounds for more streaming questions. Thank you.
Things generalized for non-constant d. Can you elaborate on that?
Oh, right. So, well, lower bounds are for constant d. Okay. Right. But upper bounds you can prove a variance bound in terms of the d, okay, and we'll lose some kind of poly d factor there. Okay. I think it's even linear. But,
okay.
So d might be non-constant, but you could still have a bound on how many triangles an edge creates, right? In that case, you could do the analysis in terms of that parameter, right?
Well, one could do a variance bound, yes, in terms of that. Yes.
Let's take Mike again.